All right, welcome to the next lecture on entanglement theory. This is a tutorial lecture series for SheQuantum, which is an organization dedicated to supporting women doing research and learning in quantum information science. Previously, we talked about the resource theory of entanglement and how do we quantify entanglement. The discussion was a bit abstract, perhaps. Eventually, we'll see some concrete examples of entanglement measures. One of the main concepts we talked about was an entanglement measure. And the main property of an entanglement measure is that it's a function when evaluated on a quantum state that does not increase under the action of an LOCC channel. Okay. So now we're going to move on to the operational approach to quantifying entanglement. The topic of last lecture was the axiomatic approach to quantifying entanglement. Okay. So what do I mean by this? Well, with the axiomatic approach, we start out with the basic axiom, and then we listed several properties that are desirable for an entanglement measure. A different approach, but it ends up having relations to the axiomatic approach, is called the operational approach. So what we do is we come up with information processing tasks that end up quantifying the amount of entanglement present in the quantum state. So it turns out that these approaches can intersect when we're trying to figure out bounds on optimal rates of the operational tasks. As it turns out, it's very difficult to compute the answer to the operational task that we'll talk about. And the best thing that we know how to do is to devise bounds on these tasks. Okay. And the most important tasks are entanglement distillation and entanglement dilution. So what is entanglement distillation? Let's start from here. And here you see that we're using the normalized trace distance. Okay. So let's unwrap this. We have something called one-shot distillable entanglement. It's a function of a quantum state rho, bipartite state rho. It's a function of an error parameter epsilon that goes between 0 and 1. So what we do is we take this bipartite state, we act with an LOCC channel, and we try to get an output state that's epsilon close to an ideal d-dimensional maximally entangled state. Okay, and so we're just trying to optimize the number d. We're trying to make d as large as possible. We're trying to extract as much entanglement as possible out of the state, subject to the constraint that the output state is epsilon close. That's the only requirement. So we optimize overall d, natural numbers, and overall LOCC channels. Okay, and to give you a sense of why this problem is hard, earlier we said how optimizing over the set of separable states is hard. Related to that, optimizing over the set of LOCC channels is hard. And so that's why this is a hard task. The distillable entanglement is an asymptotic quantity, okay? So what we do is we take n copies of a bipartite state, we evaluate the one-shot distillable entanglement, but now we're interested in the rate at which you can extract E bits per copy of the state. So this E is the number of E bits, log base 2 of D, and then per copy, 1 over n. So it's like the average amount of entanglement we can extract from the state. And then we allow for the number of copies to go to infinity, and then we also want the error to go to 0 as well. And so these two limits are there, and then that's how you define the distillable entanglement. Okay, so a way that you can describe this in a casual way is it's the largest rate at which you can extract entanglement from many copies of the state such that the error converges to zero and the limit as this n becomes large. So that's a more casual way of stating all of this. There's also something called strong converse distillable entanglement. It's a bit technical, but it's you change the limit inferior to a limit superior and the infimum to a supremum, and you get strong converse distillable entanglement. For many states, there won't be any difference between distillable entanglement and strong converse distillable entanglement. But I think in general, there can be separations between them. And you see that the strong converse quantity is always larger than or equal to this one here, because you have the supremum instead of infimum. So here's a figure designed by Sumit. He's my co-author of our book, Principles of Quantum Communication Theory, a Modern Approach. This is a depiction of entanglement distillation. This is in the chapter. We have a whole chapter dedicated to entanglement distillation where we really delve into the theory. So you have many copies of the state for Alice and Bob. They're allowed to do an LOCC channel, and they're trying to extract a maximally entangled state with the Schmidt rank as large as possible. The opposite task, or kind of the reverse task of entanglement distillation, is something called entanglement dilution. And this is where you're trying to figure out what's the minimal amount of entanglement combined with LOCC that I need to prepare a state that's epsilon close to the state rho AB of interest. Okay, so this is the one-shot quantity. It's again a function of rho and this sometimes called smoothing or error parameter. That's a number between 0 and 1. Okay, so the point is you're trying to minimize the cost needed to prepare a quantum state, and the cost is quantified in terms of the Schmidt rank of this maximally entangled state. Okay. And then the entanglement, the asymptotic entanglement cost is defined in this way. So it's again, EBITs per copy of the state. And then we have these limits as the number of copies is going to infinity and the error is going to 0. And the strong converse entanglement cost is like the flip of this, where you change the suprema to infima. Okay. There is a way to relate these two quantities. In the preparation of these lectures, this is something that I proved. It's an unpublished note. I wouldn't describe it as simple to prove, but it's kind of like a fundamental law of entanglement, right? And this kind of thing was known before this note that I wrote. It was known for the asymptotic case. I don't know if it was fully known for the non-asymptotic case. But what it's saying is that the distillable entanglement cannot exceed the entanglement cost. So the amount that you get out cannot exceed the amount you need to invest. And that's, if you study physics and like the second law of thermodynamics, it's similar to that kind of statement. Like you don't get entanglement for free. And so that's what it's saying. And then for the one-shot case, it's up to these corrections related to the error. It's up to this logarithmic correction related to the error. Like if you allow the error to be very large, then you can violate this, with this term here. Right, exactly. So it's like a second law-like statement. You cannot get out much more entanglement than we invest. And then if you want to go to the asymptotic case, we can apply these definitions from the previous slide. We can divide by n and take limits, and then this term will just go to 0, and these other ones will converge to the asymptotic entanglement cost, the asymptotic distillable entanglement. Okay. So in general, it's difficult to compute distillable entanglement and entanglement cost. That's what we argued for. We said it's hard to optimize over the set of LOCC channels. For the asymptotic quantities, it's not even known whether these operational quantities are computable in the sense of Turing. So that's a big open problem, and no one has solved it, but there's a chance that these quantities might even be uncomputable. And so given that kind of negative outlook, the best thing that we then try to do is to bound these quantities. And to do so, we can use entanglement measures. Okay, so we can establish lower and upper bounds. So an interesting upper bound on entanglement cost is the entanglement of formation. Okay, so there's a way that you can prepare a quantum state at a certain rate that's equal to the entanglement of formation. Okay. And upper bound on the distillable entanglement is something called Rain's relative entropy. So that's an interesting entanglement measure. And it limits the amount of entanglement you can distill from a quantum state. So it says like using this state, you will not be able to conduct teleportations at a rate larger than this. And that is the Rain's relative entropy. Okay. Then there's another quantity that's both an upper bound on distillable entanglement and a lower bound on entanglement cost, and that's something called squash entanglement. So that's a very interesting entanglement measure. And in the slides that follow, we'll be talking about these entanglement measures. Let's start out with a simple one, and that's the entanglement entropy. Okay. And I should mention that these slides are really based on a chapter called Entanglement Measures in the book I co-authored with Sumit Khatri. That's Principles of Quantum Communication Theory, a Modern Approach. It's available in the archive for free. Okay, so the Schmidt-Rank entanglement criterion that we talked about earlier, it's just that for a pure state, psi is entangled if and only if its Schmidt rank is greater than or equal to 2. So we can then use what's called the entropy of the reduced state to decide whether psi AB is entangled. So the entropy is this formula. This is one of the most famous formulas in all of science. It appeared in a movie called Arrival. And to calculate it, what you do is you take the partial trace over Bob's system, and you get this generally mixed state. And then this is a function of a density matrix. In earlier lectures, we talked about how to compute a function of a matrix. So you do that, and then you multiply these and then take the trace. This is called the entropy of entanglement. And what you can show is that the entropy of entanglement is equal to 0 if the pure state psi is separable, and it's strictly greater than 0 if psi AB is entangled. As it turns out, for pure bipartite states, entanglement theory simplifies a lot. So both the distillable entanglement and the entanglement cost, they're equal. That means entanglement theory is reversible in a physical sense, and they're equal to the entropy of entanglement. And that's for every pure bipartite state. So that's the story for pure states. Entanglement theory, it gets more difficult when you go to mixed states. Okay, so I think we can end this lecture by talking about entanglement of formation and its properties. So to get an entanglement measure for a mixed state, what you do is you compute this, what's called convex roof of entanglement entropy. What does that mean? You take the state of interest, rho AB, the mixed state, you find a pure state convex decomposition of that state. So you figure out a way to write it as a probabilistic mixture of pure states. And then you compute the average entanglement entropy with respect to this pure state decomposition. And then you try to make that as small as possible. So you take the infimum over all possible decompositions. Okay. And that is what's called entanglement of formation. What are its properties? I'll just state them. I won't prove them. If you want proofs, you can look in the book with Sumit. So, entanglement formation, it obeys the LOCC monotonicity, and more especially, it obeys the selective LOCC monotonicity. It's convex and it's faithful. These are properties we talked about in earlier lectures. I won't get into them in depth here. It's equal to the entropy of entanglement for pure bipartite states. And additivity was a property we talked about before. It's known to be non-additive. That was a big open problem for a long time, and it's known to be non-additive. And it's also known to be difficult to compute. In some cases, you can compute it, like for some what's called bosonic Gaussian states of interest in experiments, you can compute it. But in general, it's going to be hard to compute. We know that it's an upper bound on entanglement cost. That means, the average cost of preparing a state, an upper bound on that is the entanglement of formation. So there exists some strategy that you can use to achieve the entanglement of formation rate for this problem, for the entanglement dilution task. One thing that's also known is if you take the entanglement of formation formula and you do this mathematical procedure called regularization, that's actually equal to the entanglement cost. So that's an interesting formal result, but its usefulness is a bit limited because in general, it's unclear how you'd actually compute this quantity because it involves this infinite limit. All right, why don't we stop for there, stop for now, and we can pick up next time.